Welcome to Brain Vision.
In this question, we're looking at a hydrogen-like atom. Basically, it's beryllium, but it's triply ionized. So beryllium itself initially has 4 protons and 4 electrons. But if we remove 3 of them, it becomes a nucleus with 4 protons, but only 1 electron orbiting around it. So this is a hydrogen-like atom. Now, how do we find the ionization energy for this? Well, if you take a look at the Coulomb force, right? Basically, the Bohr model is derived by looking at the Coulomb force between the nucleus and the electron. The Coulomb force is given as 1 over 4 pi epsilon naught Q1 Q2 over R squared. In this case, for the hydrogen, the nucleus charge is just E and the electron charge is just E. So we get E squared for the numerator. However, if you were to consider the beryllium, right, the nuclear charge is 4E, while the electron charge is E. So what we get is 4E squared. Therefore, we will need to replace, right, all the E square with 4E squared, right, for all the formulas for hydrogen atom in order to apply it to our beryllium atom. Now we know that the energy for hydrogen in this case is negative 1 over epsilon naught square me4 over 8n square h square. Right, this is the general Bohr model, right, for hydrogen. Now, if you were to replace E square with 4E square, it means that this E to the power of 4 will be replaced, right, for beryllium to become m times 4E square squared. Which is equals to 4 square times the original hydrogen expression. Right, this is the energy for hydrogen. So what this means is that it is basically just taking the number of protons square multiplied by the hydrogen expression, which is negative 13.6 eV divided by n squared. Now we are ready to find what is the ground state energy for beryllium. The ground state E1 would just be 4 square times negative 13.6 eV over 1 square. So there's 16 times for the ground state energy for hydrogen, which is negative 218 eV. Now for the next part of this question, we want to find the ionization energy for beryllium. So the ionization energy is when n goes to infinity. And we see that when n goes to infinity, our energy will go to 0, which is the same as our hydrogen. Right, this is because the reference point is always at the ionization energy level. So, well, if we are referring to the same reference level, they will have the same energy of 0 eV. So since they have the same ionization energy level of 0, their ionization energy for beryllium is just 0 minus negative 218, right from the ground state, give us 218 eV. Right, compared to hydrogen, the ionization energy for hydrogen is 13.6 eV. So this is actually 16 times. Next, we want to explore the transition from n equals to 2 to n equals to 1 for our beryllium ion. So we have already determined that for the beryllium, the energy state is given as 4 square times negative 13.6 eV over n square, or just negative 218 eV over n square. We want to find what is the wavelength of the photon when the beryllium undergoes this transition, right, from E2 to E1. Be 1 minus 1 over 2 square. Now this is in terms of EV. Now to find what is the wavelength of the photon, we equate this to the energy of the photon, which is given as hc over lambda. So lambda is equals to hc divided by the energy of the photon. hc we can use 1240 eV dot nanometers, and since the energy is in terms of electron volts, 163.5 eV. This will give us 7.60 nanometers. For the last part, we want to find the radius of our beryllium for a general n value. Right, so we know that the equation for hydrogen, the radius, is E naught times n square h square pi m e square. Now remember that if you want to convert it into a hydrogen-like atom or ion, we just have to replace the e square with z e square. And in this case, our z is 4. So this for the beryllium. This radius will be just naught. So this is just 1/4 of the radius for hydrogen. Therefore, for any given value of n, right, the radius for our beryllium will be smaller by a factor of 4 compared to the corresponding radius for hydrogen.